All right, here's some kinematic equations that we already know. That was the first one that we learned. Okay, now where did that one come from? We sort of proved it when we started this. We did this with the motorcycle thing. All right, this is just the basic definition of acceleration. So another way to write it is like this. Just delta V over t. And that's the definition of acceleration, a change in velocity over change in time. Okay, then we learned how to bring displacement into the mix. Okay, so now we can deal with meters if we have that. And here's the new one today. Okay, that's the new one. You haven't seen that one yet. It's got squareds in it. All right, and what do you notice about it? What's different besides the squareds and the math and all that? What's that? Okay, this one is not solved for displacement like this one is over here. That's right. Okay, what else? Go ahead. Okay, we've got a 2 instead of a half. What variable is it missing? What does it not have? No time, okay? So we call this the time independent. Okay, time independent kinematic equation. Now, this one we showed where it came from. This one we showed where this came from, and really this is just a calculation of the area under a velocity graph. You did that in your drive lab as well. Okay, so you calculated the area without even using this one actually. Okay, now this one takes at least 2/3 of a sheet of paper of algebra to show you where it comes from. Do you guys want to do that right now? Or do you want time to work on your homework? Time to work on your homework, right? Okay, we could show it, but I'm just not going to take class time to do that. Okay, it's a really good way to fall asleep. If you're having trouble sleeping at night, go look up the derivation of that. Okay, you will fall right asleep. Okay, all right, so we'll leave that alone. I don't like doing that. I like you to know where these come from, but we're not going to take the time on that one. Okay, when can we use these? They may be used under what condition? Okay, constant acceleration. Okay, now what that means, okay, in these, all right, velocity's changing. Okay, we've got VIs and VFs all over. Distance is going by. All right, the position is changing in all of these, but we won't have a changing acceleration. Okay, to deal with a changing acceleration, what do we need? Does anybody know? It's actually the name of a class we offer at Fruita Monument. It's calculus, okay? This is algebra-based physics. We're not going to touch any calculus, okay? Once we get to calculus-based physics, we can deal with changing accelerations, okay? Adds a whole layer onto what we can do. Okay, now, this right here, in a minute, you are going to practice using these three. This isn't even physics down here. This is just like algebra reps. It's like algebra push-ups, algebra calisthenics, okay? And you're going to get a chance to make sure you know how to use these. And I'm going to give you the answers as we go along, okay? So let's number these. All right, and you're going to do these on a separate page. And you're going to turn it in with the other 10 examples down here, okay? And you're going to get a whole block to work on this in just a second. Okay, so basically, here's the variables. If you know 3, you can get the other 2. All right, so we'll practice the algebra here without the word problems. The main thing you want to know with this, okay, watch your negative signs. Okay, if you get the wrong answer, think to yourself, did I do the negative signs correctly? Okay, the other thing you want to do is watch your squareds. Squared values. Okay, if I'm walking around and someone's like, oh, I didn't get the right answer. Okay, these are the first 2 things I'll check on your work. Okay, and then the third thing is you want to watch square roots too. Okay, because let's say you want to get a V final, eventually you're going to have to square root your answer, okay, and that'll get you the right answer. Okay, now, like I said, this is just math. This is when we apply the physics down here. Okay, so we got our word problems. Don't forget your 4 steps of showing work. Okay, I kind of built those in for you a little bit here. And things we want to pay attention to. Okay, if something is constant, okay, like if we have a constant velocity, what does that mean about acceleration? It means that acceleration is 0, okay? Constant velocity means 0 acceleration. All right, when that happens, by the way, when acceleration equals 0, then you're just going to use this. You're going to use velocity is delta x over time. Okay, I'll show you that on your equations page in a second. Okay, at rest. Okay, when something is at rest, what is velocity? 0. So something can come to rest, all right, like I said here. If something comes to rest, that means that V final equals 0. If something starts from rest, okay, that means VI equals 0. Okay, uniform, that's usually used with acceleration. Okay, uniform just means constant. Okay, so just notice that in these problems, and that'll help you out. Okay, so we're going to do a few of these together. I'm going to lay out what your homework assignment and your in-class assignment is. We'll do this one together in a minute. So that's an in-class. Okay, this one, homework. This one we'll do together in just a second. Okay, let's turn to the next page. Okay, example 4 here. That one is homework. And like I said, you're going to get a ton of time today in class to do that. Okay, also on your own. Number 6 is YouTube. Okay, so that's not just for the absent students, that's for everybody. You're going to do this one on YouTube. Okay, so you go to Mr. Hicks Physics, and then you go to Kinematics playlist, and it's called something like this, example 6-8. And it'll go through 2 of these with you. Okay? I find if I do too many with you here in class, you guys fall asleep, and I don't want that to happen. Okay, so you'll do 2 at home. 7 is on your own. Eight is YouTube. Uh, 9 and 10 are on your own. Okay, so I'll check that. And you'll get a bunch of time to work in class. Okay, so let's go back to this, and we'll do 2 together here, and then you can go back up to this and work with your buddies on this. Okay, question? Yeah, you totally can. All right, I always encourage you guys to do physics together, as long as you're actually doing it together. And not being like, oh, you take number 1 and I'll take number 3 and then we'll like copy. Does that get you anything? No. Okay, so as long as you're actually working together, you can work together over the phone. Okay, what are you guys using these days? Video chat? FaceTime. Thank you. I should know that one. Okay. All right. First step when we get a problem like this is listing our knowns and our unknowns. Okay, so we've got a runner, okay, and they're basically moving along the x-axis of a coordinate system, and during a 3-second time interval, they are going from here position, okay, so this would be an x initial, and they're going to here, x final. Now in a lot of these problems, you will just be given the delta x. Let's go ahead and add a delta up here. Okay, because all of these displacements that I gave you, these are all change in x. They're already x final minus x initial for you. Okay, this one didn't do that. Okay, so let's list what we know. Time, 3 seconds. All right, and that's what we know. Okay, do we have any velocity or acceleration info? Does it say anything about them speeding up or slowing down? No speeding up, no slowing down. Okay, we just have change in position and time, and they want us to find average velocity. Okay, one way to say that we want to find an average, you haven't seen this yet, is by putting a bar over that. Okay, any variable with a bar over it means average. Okay, now you don't really have to do that. Okay, since there's no acceleration, we are just doing an average. Let's look at our equations page. Okay, do we have those out? Let's maybe put a box around the top 4 equations. Okay, well let's talk about these. So these are the ones we use for averages when we don't have something speeding up or slowing down. Okay, now the thing may be speeding up or slowing down, but we don't really care in these. Okay, it's just change in x over time or distance over time if we're talking speed. These are where we care about speeding up and slowing down. Okay, constant acceleration equations. Those are all your kinematic equations. Those are the only things you're going to use in this unit. Okay. So, here what we're going to end up using is this one. Okay? Let's draw the graph. for every problem in this packet except this. You don't have to draw the graphs for these. What you're going to do is you're going to draw the velocity graph for the situation. Okay, so we'll put some axes here, and you can finish that on the rest of them. Okay, and let's add these here. Okay, you don't have to draw the position and acceleration graphs, just velocity, because they kind of tell us the most information. All right, so on this one, we are starting at 50, and then we're going toward 0 to 30. So is this going in the negative or positive direction? This is the negative direction. And since it's just a runner going along, there's no acceleration, we're just going to say that this runner has a constant negative velocity. Okay, it doesn't mean they're running backwards, by the way. It just means they're going in what is defined as the negative direction by these values up here. Okay, so let's do our math. We're just going to go over here, and we're going to do final minus initial. And we'll divide by the time it took. Let's take out our handy calculators and punch it in. Okay, so there's our answer. If we know the rules for significant figures, we put an extra 0 on there to show accuracy, because we got 3 sig figs and everything. Okay. You guys can do this one on your own. Notice we got kilometers per hour here. This one, the how far, let's answer in kilometers. Okay, that way we won't have to convert. Okay, last thing I'm going to say today, and then you have some work time. Number 3 here. Okay, we've got a car accelerating on a straight road from rest. Okay, I like to underline things like that. 275 kilometers per hour in 5 seconds. Okay, what's the magnitude of its average acceleration? And we're going to do this one in meters per second squared. So you notice that our speed and time values don't agree, because this is hours, this is seconds. We're going to have to deal with that. Let's list our known data. Okay, so first of all, VI equals 0. V final, kilometers per hour, that's 75. And our time. Acceleration is the value we want to find, so we're going to put question mark. Oh, thank you. It is meters. Yeah, we could put either, because we're going to go to meters per second. I'm going to leave it as meters per second. That's a good, you could put either right there. Okay, I'm going to actually leave it, because I'm going to take this to meters per second. Okay, now over here, that's what we're going to do first, is get our units right. So question mark, meters per second is equal to, and we're getting pretty good at this. We did a really nice job on our unit conversion quizzes. And so we'll set it up like that. I always like to convert the top unit first. So let's lay this out. We're going to go kilometers here. And in one step, we can go directly to meters. We may have this one memorized. Okay, 1 kilometer, how many meters? 1,000. All right, kilometers is gone. This was one thing some of us struggled with on our quizzes, is converting the time. So hours here, and we can go directly to seconds. Okay, we can skip the minutes thing. Okay, so if we have 1 hour, it's 60 times 60, so 3,600. And we can cancel. Okay, so punch that in real quick. Okay, so now we have a V final. Notice it says equations. Sometimes we need a couple equations. This is a sort of an equation. It's a unit conversion. Okay, now down here, our second thing we're going to use is delta V over T. All right, or you could use that one. I like this because it's already rearranged for me. Okay, so the final 20.8 minus the initial, and this took 5 seconds.